اوكي. صباح الخير شباب وشابات. اليوم ان شاء الله my plan to finish to complete the relay evolution. So I have reached to the last part where I have already explained about the protection microprocessor based relays construction. Okay, so this is one of the commercially available relay, ABB relay. This is what's inside. They have DSP port, okay, and they have microprocessor controller there. And they have inputs to those DSP ports. So we have analog inputs, which are phase A current, phase B current, phase C current, phase A voltage, phase B voltage, phase C voltage, and zero sequence current and zero sequence voltage. Okay. Zero sequence current is the summation. When you have a summation CT, it gives you the the zero sequence current. And if I have a star delta transform VT, if I connected the primary side star, secondary side open delta will give us the zero sequence voltage, which is summation of the three voltages gives you the zero sequence voltage as inputs. Now I have 8 channels here for this relay, and I can have also as a binary input or output, which is binary output mean digital outputs, or the tripping. Say a trip signal is an example of a binary output. Binary example, it could be like a trip signal came from another relay informing this that it has tripped, or binary input could be also status of the breaker. Is it it is closed or it is open? This is only high or low inputs. Okay, so we call these binary input and outputs. And we have also communication where I can send probably a signal through a communication channel to another relay, okay, through transmitter and receiver communication module. I have also sometimes a relay can receive also analog input instead of currents and voltages. I can send let's say relay can receive, let's say, the temperature of the transformer winding, of a motor winding. So we have a transducer that change that temperature to, or sometimes whatever signal I have, from 4 to 20 milliampere module that correspond to a temperature from, let's say, a range of temperatures. So then I can also receive it, okay, as inputs. So based on these inputs, relay will decide is there is a normal operating condition or it's an abnormal or short circuit conditions. So all the protection and measurement functions are built within the DSP board, and these only control the which input has to come first, okay, and so forth. I can have also Ethernet inputs to a relay. I can have inputs from a GPS antenna for time synchronizations and so forth. Numerical relays, as I mentioned before, the heart of it, the microprocessor, but inside microprocessor we need to program it, and these programs we call them algorithms. Okay, so what's algorithm are a system of mathematical operations, okay, to be implemented in a program to do a function. Okay, to do a program, or to, let's say, to estimate, let's say, the voltage magnitude or its phase angle, I need to have samples of information. So we need at least n number of samples. Okay, n where here could be 3 samples, could be 10 samples, could be more. So it depends on the algorithm, accuracy algorithm. I need to know, I need to have a set of n samples from the input signal in order to perform the operation required, in order to estimate the voltage magnitude, for example. Okay, once I estimate the voltage magnitude or current magnitude, then I can decide is this a fault condition or not by doing a comparison. Okay. Um, Now this is like a flow of signal. Let's say suppose the first thing I will read the current sample, the current analog input to me, which a current or a voltage. Then I will do sometimes a digital filtering. Okay, I will eliminate, for example, a DC or unwanted harmonics from the signals. Then I want to estimate the phasor. The phasor is the fundamental voltage, magnitude, and its angle. Okay, and current also magnitude and its angle. We call it the phasors, right? Phasor is a signal of a single frequency. And we want to, once we estimate the magnitude and voltage of the 50 hertz, the fundamental, or 60 hertz, if we are working in Saudi Arabia, for example, then we can decide, therefore, what do you want to do with these voltage, magnitude, and current magnitude and angles? Do you want to divide them? You want to compare them with the settings, or you want to? This is the protection function you want to implement. And then once you compare this measured voltage with a setting or whatever, then you take a decision, right? A logic, okay? What's the decision you want to make? Do you want to trip, or this is a normal operating condition, then you want to take another new sample, a new reading, and you go over this. I'll show you here in the following a digital filter. Like here, I have input samples. This is something like a distorted signal. So the signal this is analog signal which has some harmonics in it. This is the analog signal. Okay, and it is sampled. So the star points represent the sample value of this analog signal. So this is after, let's say, A to D converters. Okay, after the sample and hold and convert it to corresponding analog values. This is the sample values. Then once you pass it through a digital filter, I can get rid of the harmonics. So I got only the fundamental. Okay. Or sometimes I want to only remove high frequency components. So in digital filters, what are filters? We have analog filter and digital filter. Analog filter where you can have active or passive filters. I can use RC as a low pass filter. This is an analog filter, right? A low pass filter, RNC. But can I make a low pass filter using digitally? Right? From the sampled value, I can implement it. Yes, you can. Okay, without using hardware components, just a software. I can use a band pass filter or high pass filter or okay. So you can. These are called digital filters rather than. You can also implement this using op-amps. We call them active filters in this case. So digital filters are filters that extract a specific information or remove something that you don't want it, but that is made digitally, okay, by using an algorithm. So to implement digital filters, now in protection, what I want to do, I want to estimate the magnitude of the voltage of the 50 hertz component and its angle. So I need a filter that filter all harmonics and accept the fundamental. Or sometimes also I want to measure the second harmonic only, okay? So I need a filter that measures only the second harmonics, okay? Magnitude. So I need to, in order to implement digital filter, I need a samples, a number of samples, okay, of the input analog signal. And those number of samples that you will use to find the fundamental, we call it a set of a window, a data window. Okay, so it's a collection of samples. For example, here I have this 3 samples. Okay, this is the red one is the newest in the window, and this is the oldest. And I want to use these 3 samples, 1, 2, 3, these to estimate the peak, this peak that will come, okay, of this signal. Now this is called, now this I can use 3 samples or I can use 5 samples. Now some algorithms use 3, some samples algorithms use 2 to estimate this peak. Okay, I can predict this before they come. Okay, so this is a sort of a window. Now once from these 3 samples I estimate this, and once a new samples comes in, I will remove the older one, and I keep, you know, estimating at once each samples comes in. Okay. So I'll show you now how do we estimate the peak from 3 samples only, and how estimate the phase angle of this signal from 3 samples only. So we have so many algorithms. This is the simplest one, which was a long time ago used when the microprocessor speed are slow and the memory are also low. So in this algorithm, suppose I have a sinusoidal signal, okay, and I want to estimate its peak. So the sinusoidal signal, and I'm assuming in this algorithm that the sinusoidal is a pure sine wave, okay? I have no harmonics in it. So what I wanted to estimate, I want to estimate this peak of the signal. So this is V of t, okay? Function of time. I want to estimate its peak, and I want to estimate the phase angle. I know this frequency is 50 hertz, 2 pi f, no? So f is known to me. I'm assuming this is a 50 hertz. So in this algorithm, I know the frequency is assuming it is 50, known, it's not changing. But I want to estimate this and this. Based on 3 values of V of t. So let's call these 3 values. One value at time is measured at time 0. So like this is t0, and this is t1, and this is, let's say, t minus 1 or t plus 1. So what t plus 1 means now, t0, let's say at our reference at time, let's say 0. So what's the corresponding time at time 0 is when t equal to 0, v of 0 is equal to v sine of 0, so it will be sine theta, okay? And one sample after this time, you know, once we sample this analog signal to by sampling and hold, so we have these three values, and they come after each delta t, and delta t is the sampling time. This delta t is 1 over fs. Fs is the sampling frequency. So at each interval delta t, I'll have one sample. So this time represents t naught. This is t naught plus delta t. And this time represent, let's say, this time represent, which is t minus 1. Let's say this time represents t naught minus delta t. So if delta naught is, if t naught is 0, this is minus delta t, and this is plus delta t, the plus 1. So plus 1 means one sample ahead, minus 1 is one sample before, okay, the present sample. So I call this value of v of t at t naught, I'll call it v naught, and the value of the sample magnitude at, okay, or sample value at t1 plus 1, I call it v plus. So it is v plus here represent the v at time t naught plus delta t, okay? And similarly for t minus 1, okay, at time t minus 1. So if I have these three values, so this and this and this three, can I estimate this VB and theta? Yes. Okay. So how do we do it? First of all, this is V of t. This is V of t. Okay, which is the we want to. Now let's assume what is the voltage V of t at time 0. Okay, is when t0, I'll get this. This is first equation. And second equation is now if I take the derivative of this, okay, what is the derivative of this? dV by dt, it is VB cosine omega t plus theta times omega, right? And from that, at time 0, this derivative at time 0 is equal to omega VB cosine of theta. So I have a second equation. Okay, and this is the first. Now, dV by dt is a slope at time t0. So how do you find the slope digitally from 3 samples? I can estimate the slope at t0 by a tangent line. Okay, so how do I estimate? I have 3 values. To estimate this, I can take the slope of this triangle, right? By using an approximation. So I want to estimate the slope here, d v naught by dt by using this triangle. So what's the slope from this angle? So this is approximately, okay, v, this is the height v plus, right, minus v minus, which gives me this, right, divided by the time, which is this, 2 delta t. That gives me an estimation, approximation to the derivative at time t0. So this one can be estimated by this. Okay, so that part. And now I can replace this left-hand side with this and can arrive to the following equation. Can arrive to this, right? I can substitute this here so that VB cosine theta becomes this divided by omega. Okay, so from these two equations, 4 and 5, I got this. So this is one thing. This is star with star, and I'll put here star. So from these two equations, I have VB sine theta equal to V naught, and V naught is known to me, which is the value at here. And VB cosine theta is equal to, this is known to me, this is known information, this is omega is known to by F, delta T is known to me, because I know the sampling frequency. And so from two equations, two unknowns, I would like to find VB and sine theta. So how do you find VB and sine theta? If you square, so we have two filters. Let's say we have two filters. This represents the imaginary part of the phasor. Why we say this is in phasor domain, this is V equal to VB, okay, angle theta in phasor, okay, representation. This is a vector, okay, and so this is like VB cosine, right, theta plus J VB sine theta. So we call this the real part, real filter. The imaginary part, which is VC, is the imaginary filter. Okay, so two filters will estimate the phasor of this. Okay. Now this is the real filter VB sine theta, which is V naught, and VB cosine theta is the imaginary. Okay, the real part. Sorry. Okay, this is the imaginary part. All right, so from these two filters, I want to estimate this, V and B. So how do I find V? I'll square this plus square of this and add, and that will eliminate, right? Sine square plus cosine square, it will be 1. And then I'll get VB square. And this will be like, right? This will be then V square plus all of this square. Okay. So if I square this, I'll get this one. If you square this side plus 6R square, I'll get this VB square. Now from this, to get VB, I'll take the VB equal to square root of this. So I can, from these three samples, I'll be able to, this is delta T capital. From these T samples, I will be able to estimate the peak at any three samples. And similarly, I can estimate the angle. What's the angle? If you divide this by this, so VB cancel, sine theta over cosine theta will be tan theta. Tan theta equal this over this, okay? And from which I can estimate the angle theta, okay? So from these two filters, I will be able to estimate VB and theta. Now, based on the assumptions that the signal is a pure sine wave, has no harmonics in it, and I know its frequency. This is the assumptions. Now let's take an example to illustrate this. Suppose I have a frequency of 60 Hertz, and this signal is sampled at 720 Hertz. Okay, this is Fs. So delta T is 1 over Fs, the sampling time. Sometimes we call this also Ts, the sampling time, or sampling, okay, interval. And omega delta T, you say 2 by F times delta T 1 over 60, it will be pi over 60, okay, which is correspond to 30 degrees. So what are these two filters I want to implement is these two. So VB sine theta equal to V naught, and VB cosine theta equal to this, V plus minus V minus over 1 over 2 omega delta T. So when I take 1 over 2 times 2 pi times 60 times 1 over Fs, that gives me this number, 0.955. So this is 1 over 2 omega, okay, delta T. Give me this. So I can calculate this priorly. So I have these two digital filters that I need to program inside the microprocessor. And each three samples I get in, I want to estimate these two quantities. From these two quantities, I want to estimate then VB and theta. All right. So this is my algorithm. Now let's assume now. I'll show you now. If I have, I'll show you. And I did it in Excel. So what I did, I took assume this is a fundamental 60 Hertz, sampling frequency 720. Can you see this clear? Is it clear for you?
Yes, doctor, yes.
Or I have to make it bigger?
No.
واضح? Okay. So sampling frequency 720 Hertz. Amplitude, suppose I have a signal of peak 10. I want to estimate that 10, okay? And the phase angle, I assume it is zero. There is no phase shift in the signal. And so 1 over, I need to find 1 over 2 omega delta T because I have it, I need it in the, okay, I need it here, right? I need to find this 1 over that value, 1 over this, okay? So I want to find it. So I got calculated already 1 over this. I got it. This is this is not changing with time. It is only one time calculation. Okay. And sampling frequency is 1 over, which is delta t, 1 over fs. So I divided 1 over this. Okay. So how many sample do I have per one cycle? If you divide fs, okay, if you divide fs by f fundamental, it gives how many samples are there within one full cycle. Now I have 12 samples per cycle. Now the signal, I am assuming now signal is of this form, V peak, I'll say this is VB instead of Vmax, V sine omega t plus theta, and theta here I said. I made a general program. So I have now assume I have sample 0, sample 1, sample 3, sample 4, and so on. At each sample, I assume the 3 samples are 0. So I will start like I have no faults or normal, there is no current, then suddenly I have a sine wave. Okay. So from here I started implementing this, the magnitude, which is the 10 sine 2, which is omega 2 by 2 pi f, the frequency 60, okay, over times delta t 1 over the frequency, okay. So I implemented this equation. So by multiplying each sample by this. And then I implemented, so this is the signal values at each sample. So it is like the instantaneous value of this signal at each moment of time. So, all right. So then I have to implement the digital filter. What is the two digital filters? I have the real part. The real part is this. I have to, and the imaginary part is V naught. The real part, how do I implement the real part? So what's this equation? If I want to estimate the sample at 5, the voltage V peak at sample 5, I assume now this is my V plus, this is my V0, and this is the V minus 1. So I have, this is the recent sample, this is the one sample before, one sample before. So this is the middle sample. So the middle sample is represented as V naught. So the real filter is V plus, which is this, minus this, V minus, divided by or multiplied by this 1 over 2 omega delta t by this factor. Okay. And so this is the filter, real filter. The imaginary filter is V naught. V naught is the middle one because this is V plus, V0, and this is V minus. Okay. And so I got the real and the imaginary filter. From here I took the magnitude of this square plus this square under the square root give me V peak. And the angle, the tan inverse of the imaginary part over the real part. And I convert it to degrees by multiplying 180 over pi. And so as you can see, the input signal I bought 10, I should estimate 10, right? And if I look to the graph here, this is the sinus. The first 3 samples are 0. I put them, then I put a sine wave of 60 hertz. As you can see, the algorithm is tracking, the magnitude. So the algorithm 3 samples. This is the first sample, second 3. Once the 3 samples are completed in the window, I'll be able to estimate the peak before it comes. Okay. So this is the peak. And it stays as the new samples comes in, because the peak doesn't change, so it will stay same. So I'm estimating the peak of the signal. Similarly, I estimated the angle of the signal. So the first 3 samples are 0 then one sample comes in, it estimates the angle. Now what's the angle at peak is 90 degree. So here is the 90 degree. Now, what's the angle when 0 crossing at this? is 180 degree. Okay, and what is the angle here at this point? It is 360 because and here we have only up to 180, then change the angle to negative. So once reach 180 degree, it will go change to minus 180 and continue. Okay. So this is the angle of the signal that varies with time. Okay, so if I change now, if I change the magnitude to, let's say, 20, will it track this? Okay, as you can see, it goes to 20, right? Estimated. If I change, yes, any question? If I change the sampling frequency, so now I'm using 12 samples in one cycle. What does 12 samples per cycles means? Within one cycle, I have 1, 2, 3, 4, 5, 6, 7. So within one cycle, I have 12 samples of informations. But I use only 3 of those 12 samples to estimate the peak. All right. Now, suppose I increase the sampling frequency, okay, to instead of 12, I go to 20 times. 12, I have instead of 12 samples, I want to get in more sampling frequency. So I'll increase it to double, or to, let's say, to 20 times. 20 or double. The double is instead of 12, I'll go to 24, to this correspond 1,200 hertz. So what do you notice in the, it's almost, okay. So this is first sample, this is second, this is third. So even I estimate the peak before it comes, right? And it is almost straight line, okay. So if you go higher sample, you reduce also the errors. Now, what if I go to lower sampling rate? Let's go to 600 hertz. 600, let's go even lower. I will go to 6 times 60, which is 360 sampling rate. I have a higher error, okay? So even if you go now to, let's say, I have 60, what if I do the sampling 2 times this, which is 120, larger errors. You see, your algorithm will get confused. So number of samples is not sufficient. So you have to increase them to have better estimations. So I can study the effects of the sampling rate on the performance of the digital algorithm. So I'll go to the higher the better. So I'll go to 12,000. But you cannot go extremely large so that your microprocessor has no sufficient processing time to compute the 3 calculation within that very short time. The higher the sampling rate, the smaller is delta t. So you have to compute this calculation. You take a square root, you take magnitude square of both signals. You have, I have to estimate these two in very fast way, right? If you have very short time, okay. So that will limit, based on the microprocessor speed, it will limit your ability to take higher sampling rate. Although higher sampling rate is better, but you have to look at your processing speed, DSP, microprocessor-based speed. And now I'll show you now, if we increase, now if we add harmonics to the signal, this is like a pure sine wave. This is, I added a decaying DC, a signal with a decaying DC. So added sine wave plus a DC, decaying DC in it. And I sample it, see this is I supposed to get 10, but because of the DC, the estimated is, okay, has estimation error, then it settles to 10 once the decaying DC vanishes to 0. And when I add a second harmonic, so the signal is V big sine omega t plus another second harmonic, which is added. Okay, this is a signal of 10 peak fundamental plus a second harmonic, and this is the output of this algorithm. I supposed to get 10, but it is varying. So that makes this is not efficient algorithm if the signal is not pure sine wave. And why is this? Because all our derivation that we made, we are assumed the signal is of a single frequency. So in order to apply this, I have to do an analog filtering first so that only 50 hertz passes, and then I can apply this algorithm. That's why it is not now, it's not used in nowadays. Now we have other types of algorithm that can eliminate even this effect of DC or harmonics in the signal. So this is how fast, if I have a sine wave which represents, let's say, my load, then a fault occurs, how this algorithm tracks the signal changes. So initially I added 10 volt or 10 ampere, then I change it to 50 ampere. Okay, so it is estimating 10 first, then jumps to 50 directly. Okay, this is very fast within 3 samples. So advantage fast algorithm is very few calculation to respond, but disadvantage disadvantage of this simple filter is affected by noise and harmonics, and affected by decaying DC. As a result, it is not nowadays is not used. So we use most of the protective relay use DFT, digital DFT, discrete Fourier transform. Okay. With this, I would like to close this chapter. Okay. Do you have any questions? No questions. So this is now what we call algorithm. Okay, algorithm is or digital filters. That a digital filter, this filter estimate the peak and its angle. So when I estimate the peak and angle, I can then check, is the voltage peak greater than the nominal voltage, so I can detect over voltage. Or I can divide now the estimated voltage and estimated current, and I find the impedance, okay? And I check this impedance with the impedance of the line to check if there's a fault within the line or outside the line, and so forth. There's so many applications. I can estimate the frequency. There are algorithms that I can check whether the frequency of this signal. Is it 50 hertz, 60 or 60 plus or minus, whatever. So this is an extremely large topic. I can give you one full course on just digital filters, okay? If you have no questions, I would like to stop this one. I'll stop this recording.